Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Terrence Deacon. He is currently professor of anthropology and member of the cognitive science faculty at the University of California, Berkeley. His theoretical interests include the study of evolution-like processes at multiple levels, including their role in embryonic development, neural signal processing, language change, social processes, and focusing especially on how these different processes interact and depend on each other. Professor Deacon's research has combined human evolutionary biology and neuroscience with the aim of investigating the evolution of human cognition. He is the author of The Symbolic Species, The Coevolution of Language and the Brain, and his most recent book, Incomplete Nature, How Mind Emerged from Matter. And this book explores the relationship between thermodynamic, self-organizing, evolutionary, and semiotic processes, and provides a new technical conception of information that explains both its representational and normative properties. So, Dr. Deacon, welcome to the show. Thank you a lot for accepting the invitation.
Thank you.
Okay, great. So I would like first to ask you, how did it happen that you got into a position where you have sort of an interdisciplinary approach to these many different subjects that I talked about in the introduction? Because if I'm not mistaken, you studied several subjects spanning from physics to anthropology. So how do you present yourself academically, and how did you get to that point of an interdisciplinary approach?
Well, largely it's because of my background and because I've changed my interests over time. I actually began my studies as an undergraduate student in physics, but became much more interested in biology after that, in that process. But it was really in the late 1970s I came across the writings of a philosopher, Charles Sanders Peirce, end of the 19th century, beginning of 20th century philosopher, that really caught my attention. And as a result, I went as a graduate student to Harvard to study his works, because his unpublished works were hiding in a library at Harvard at the time. But I was actually not able to get to them because they were so carefully protected. And I ended up shifting to the neurosciences and eventually to anthropology as a graduate student. Studying at the time, the anatomy of primates. It was related to the anatomy of human brains, particularly with respect to language. But of course, that background, the background coming from physics, coming from basic biology, evolutionary biology, and so on, and then leading me through this, I was constantly interested in how brains develop and evolve. The result is, in the 1990s, I began work with another colleague, Ulla Isaacson, studying neural regeneration and transplantation. And we did some studies taking fetal neurons and transplanting them into other species' brains. Eventually, one of his interests, of course, was to develop a therapeutic procedure. So I've sort of pursued that for a while, and then when I moved to the University of California in the early part of this century, I decided that I would go back to my original interests. And so what you see in my career, in effect, is changing from topic to topic, but continuing the thread, allowing the thread of what I've learned before to sort of follow after me. And so that's my interests reflect a circuitous background as well. I was lucky enough to not ever fall out of favor because of my flitting from topic to topic.
Mm-hmm. Yes, that's very interesting. And so now you are a professor of anthropology. Would you say that anthropology is a discipline that gives you some space to have an interdisciplinary approach that perhaps other disciplines would not?
To some extent. I think that when I began in the field, I was talked into anthropology in part from a sometime mentor years and years ago named Gregory Bateson, who was an anthropologist. And basically he said, whatever you want to do, you can probably do in anthropology, given what your interests are. I think that to some extent anthropology has wandered away from that. It's become more entrenched in both the biological side of things and the cultural side of things, so that people on both sides of that sort of two cultures divide don't tend to talk to each other enough. I wish it was more so. The cognitive sciences, on the other hand, have become much more accepting of that kind of interdisciplinary work. And so my role as a cognitive scientist as well has allowed sort of all of those sides of my thinking to become relevant.
Very well. Okay, so now let's get into some of the main topics of your latest book, Incomplete Nature, and try to build up from physics to the human brain and also societies and mental processes and things like that. So would you say that perhaps one of the main things that come from physics that people have to understand to really understand how biological systems operate is the second law of thermodynamics and how biological systems deal with it?
It clearly is a central part of the problem. I mean, the real issue is that the second law of thermodynamics is so ubiquitous in the world. And of course, at the macroscopic level with molecules and creatures of our size, it is the major force. What I think is both the relevance of it and the intellectual danger is that we sometimes think it's the only problem to deal with. So a lot of very, very prominent work in the area of the origins of life and this relationship between physics and chemistry on the one hand and life on the other hand has been about the generation of order and the prevention of breakdown and dissolution from the second law. But in fact, I don't think that's the critical story. And the reason I say it's a distraction to some extent is because we then have become very focused on what processes that are sometimes called self-organizing, processes that generate order at the cost of pumping disorder into the world, so to speak. This kind of idea actually dates back to Erwin Schrödinger. But the fact is that that's not the whole story. It's not just that we're orderly, that we not only are orderly, but we maintain order over a long period of time. And our bodies, all the way down to bacteria, are in the process of not only doing that, but seeking environments that help us maintain that order and helping us preserve the order that's there despite the fact that conditions have changed. And I think that the one feature that maybe distinguishes physics and chemistry from life and mind is not just order, but it's what I call normativity, or what the philosophers call normativity. That is, in physics and chemistry, they're not good or bad things. They're not things that work or don't work. They just happen. But for living things, there's good or bad conditions. There's things that function and fail to function. This transition to the normative world, a world where you can have sort of things that work, don't work, or right or not right, or accurate or inaccurate. These are not things that happen in physics and chemistry. These are things that life brings into the world. And so part of my work was to say, no, it's not just the second law. The second law is absolutely important because it's where everything has to start at this level. But it's not defeating it, so to speak, using the second law against itself the way life does, is not the whole story. And I think we've stopped prematurely by looking at just that.
Okay, so in your book you talk a lot about the notion of absence and, as I understand it, how constraints work toward organizing the physical processes that then give rise to higher order phenomena, let's say, like some properties of the mind. So could you tell us about the notion of absence and also how constraints work?
Right. So the notion of absence is linked to the notion of constraint, obviously. And absence is sort of a generic and somewhat philosophical and abstract way of talking about things that are constrained, things that don't happen, things that are prevented. And so in one sense, I use the concept of absence almost as a springboard to talk about it more technically a little later in my work. But the key issue here is that everything I just said about normative features, features that have sort of two sides to them, a polarity to them, is that it's always about something that is not exactly there. And I begin the book, for example, talking about absence and the concept of zero, for example. And the issue is that all of life, because of the second law of thermodynamics, is continually dealing with the potential for things to become absent, order to break down, raw resources to not be present, and so on. And so organisms are always working against this tendency to lose stuff, to become absent in some way or another. Literally, the biggest absence, of course, is not existing. And so we're always sort of, to use Darwin's phrase, the struggle for existence. It's what life is about. But it's not just existence and struggling with other organisms. It's just to stay ahead of the second law of thermodynamics. And so absence is always a part of us. But I think we also recognize that in terms of just thinking and thought processes themselves, it's about things. When we say something is about something, what it's about is not it. So if you think about just a word, the meaning of a word, it's nothing that's intrinsic to the word. It's something that's literally absent and yet brought into focus by the presence of that word. But the same thing is true of a thought. And of course, this idea has been around for a long time, particularly since the 19th century, when the concept of intentionality, which is basically being about something, becomes a sort of major influence in the philosophical thinking. How is it that, everything that bodies do and brains do is about something? Organisms' adaptations are always about the world and about things that might happen but haven't happened. And of course, in the process of reproducing, everything that an organism is doing is about something that hasn't happened yet. So the future, the absent future, the not quite existent future is critical. The problem that I was trying to deal with is, how does physics get organized around things that aren't there? How do physical processes become organized around things that are not yet happening, or could happen, or are in need of prevention? And that's what life is all about, all the way down. But it means that that's also what life is about at the level of mental activity as well. The thoughts I have are not in my brain. The aboutness of my thoughts is not stuff going on in my brain. My brain is giving me access to it, but it's not there. So there's a troublesome not there issue that sort of has to be taken into account. And I think the real problem is that that come from a materialist sort of physical perspective only want to deal with stuff that we can put our hands on, that have intrinsic properties, that are there. But what I wanted to focus people's mind on is that, in fact, when we deal with life, we have to pay attention to what's not there as well.
Mm-hmm. And so would you say that not biological, but physical constraints are what allow for life chemistry to go through these self-organizing processes that then lead to order, for example?
Yes. So clearly, one of the things that does happen to make things self-organize is that constraints, limitations, and biases can multiply under certain circumstances. And simplest kinds of examples are things like whirlpools in a stream. A whirlpool forms because there's a bias. Say a stone is dropped into the stream that's large enough to distort the flow, the laminar flow. And as the system tries to reorganize itself, it's simply the water moving downhill, so to speak, what happens is it forms a sort of regular circle for the same reason that those things that are not flowing circularly tend to get in each other's way. That, in a sense, the flow is simpler if it flows circularly. And so over time, you drop the rock in the water, and initially it creates turbulence, and the turbulence resolves itself into a regularity. And what's happened is the constraints have all aligned and become organized and allow the flow to, in effect, be more efficient downstream. So to some extent, self-organization happens as a result of these kinds of constraints multiplying and compounding on top of each other. The problem is that's not enough to explain life. Life has to have that happen, but that's not enough. Because what you need is something like a whirlpool that, when you take the rock out of the water, keeps itself going somehow. Self-organization requires all of it's sometimes called self-organizing, even though there's no self to do it. What we mean by that, the prefix self under those circumstances, is that, in a sense, it's not forced into this regularity. The regularity sort of spontaneously develops. But when we talk about organisms, everything is about self. They're defending themselves, they're reproducing themselves, they're feeding themselves. This notion of self now is not just metaphoric, like it is in the phrase self-organization.
Mm-hmm. Okay, very well. So also in your book, you spend a lot of time dealing with some other concepts like homeodynamics, morphodynamics, and teleodynamics, and I think these concepts are very crucial to the thesis you put forward in your book. So could you explain to us each of them and how they basically work?
All right. What I wanted to do, and what this is about, is to talk about the steps from thermodynamic processes to living processes. And my original comments today were to suggest that just getting order is not enough. There needs to be another step that we've tended to ignore. And so I came up with these three terms to sort of capture the transitional steps. And the term homeodynamics are about dynamical processes of change that tend towards homogenization, hence the term. Most thermodynamic processes, particularly in closed systems, but also in a lot of open systems, tend towards homogenization. They tend towards evening things out. I wanted to use a term different than thermodynamics, in part because there are other processes that we wouldn't necessarily automatically jump to with thermodynamic processes. So, for example, even at the atomic scale, we talk about, for example, lasers, in which you pump up electrons to a higher energy state that's unstable. And what happens is that over time, they give off energy, the electrons fall down to a lower energy state in producing the laser light. But that lower energy state is not going to be easily described as thermodynamic. And yet it's, in a sense, it's going down to, you might say, a lower energy state. It's homogenizing. It's harder to go to a lower energy state, and then it goes to its bottom state. Well, to some extent, thermodynamics is about going to this evened out state so that things can't go any more even. When we say something is in equilibrium, that's what we pretty much mean. Or what we say also, it's at maximum entropy. Maximum entropy is also a state that it takes work to push something out of it. Just like it takes work to push an electron out of its lowest orbital. So I use the term homeodynamics as a sort of broader generalization in which thermodynamics is a major part of it. And with respect to life, thermodynamics would be enough because we basically don't have to deal with some of these quantum effects and so on. The term morphodynamics I wanted to use to talk about what are typically talked about as self-organizing processes, as I just described them. And the term is meant to say that these are dynamics that tend to fall into forms, form. And so a whirlpool is a morphodynamic process. But also, so is the growth of a snow crystal a morphodynamic process, or the growth of what we call convection cells in a heated liquid, heated oil, for example. You get these regular convection cells in which fluids are moving in very precise and sometimes precisely hexagonal columns of fluid and so on, simply because of the close packing of this sort of dynamics. These are morphodynamic processes, but crystal formation, like in snow crystals, but in any kind of crystal, is a morphodynamic process. It's a process in which going towards a more relaxed state, something becomes more orderly. Now, it turns out that a whirlpool is a good example of a state that is orderly despite the fact that it's constantly changing. And some of the most interesting morphodynamic processes, and those that are relevant for life, are states of constant change that are orderly. Normally, when we think about perturbing systems when they're in constant change, we think about them getting more chaotic. Turns out that chaotic processes are using some of the same dynamics, but they're in the case that, in a sense, they continually undermine any kind of regularity. It's those subsets that become regular that we're interested in life, because life requires regularity. The problem, as I mentioned before, is that regularity by itself isn't enough for life. Regularity can form in simple physical and chemical systems, like crystal growth, or like catalytic processes, and I talk about what we call autocatalytic or circularly catalytic processes, where one catalyst aids the production of another catalyst, which aids in some way the catalyst, the first catalyst's activity, so that you get things that become more organized, farther from equilibrium. That is, they sort of go in the opposite direction than homeodynamic processes. The problem is that since they are totally dependent on the external world, or that is like the whirlpool is, or have to get frozen so there's no more change like in a crystal, that's not going to be sufficient for life. What living things need to do is that they need to maintain these morphodynamic processes, but stabilize them. And what I realized is that that's going to require an additional step, an additional kind of dynamics. And I realized that the only way that can happen was that if two or more morphodynamic processes each produce the boundary conditions that the other needs. And if you get that kind of circularity of morphodynamic processes, you now have a system that maintains and stabilizes itself. Because as each system moves towards equilibrium to break itself down, to dissipate, the other system will create the environment that maintains it, and vice versa. And so you get this reciprocity of morphodynamic processes, and I called that teleodynamic. Teleodynamic because it now has a sort of intrinsic end, a telos. The intrinsic end is self-maintenance. It tends to maintain itself despite disturbance. And that, of course, is the key to life. But because of that, because a living system or a teleodynamic system by itself is supported morphodynamically, supported by non-equilibrium, far from equilibrium processes that maintain order, it must constantly be also interacting with its environment. It must be taking advantage of its environment to maintain itself somehow. And that turns out to fall out spontaneously so long as you have these reciprocal morphodynamic processes. And that reciprocity, I think, is what makes life possible. It can happen by accident. It can initiate by accident. Not easy. Morphodynamic processes are rare in the world. most things go to equilibrium and regularities break down. And teleodynamic relationships should be even rarer to spontaneously show up. And yet the difference is that because a teleodynamic system, like a living system, is self-maintaining, it organizes itself to preserve the regularities. It will tend, once it exists, to spread and reproduce itself, to generate more of the same. And that's what we see, of course, with life. Even though life is utilizing processes that are probably in the global universe extremely rare and rarefied. As soon as they start where conditions are right, they'll spread and they go all over the place, precisely because they have this additional feature, what I call teleodynamics. That is, they're directed towards their own ends. They have, in this case, there can be things in the environment that are good for them and bad for them. Their internal dynamics can be functional or malfunctional. So now once you have this reciprocity of morphodynamic processes, of self-organizing like processes, once you have it, you also have normativity, that missing piece that I suggested we've missed out on, we haven't paid attention to.
Mm-hmm. Okay, very well. So just before we get from those, let's say, strictly physical processes up to higher order mental phenomena, let's say, I just wanted to ask you this, because at a certain point there, you refer to the fact that perhaps it's a bit unfortunate that because we nowadays have this naturalistic approach that sometimes we only are worried with the things that we can get our hands on directly. But I mean, I think it is important for people to understand that, and I think that most people don't know about this, that nowadays in physics, and from for several decades now, I think, information is also treated as something that exists, right?
Right. I think, unfortunately, the term information has lost its classic meaning, its traditional meaning in the sciences and in technology. In fact, there's a chapter of the book I'm working on now that's called How Information Lost Its Meaning, which happened just at the beginning, the middle of the last century, particularly under the influence of a man named Claude Shannon, who developed what was then called the mathematical theory of communication. He actually warned against overusing the term information in a technical sense, to talk about information in all possible senses. But what we normally think about information, it's about informing, creating form, generating form, in a sense, creating in my mind, in your mind, by conversation, a new form, transmitting aboutness. So the term to be about something in English is, of course, totally appropriate to the concept of information. When somebody provides me with information, it's usually about something. And for me, I can add something in addition to that. Is it significant? Is it meaningful to me? Is it useful for me or not? And it's only its aboutness that's useful. On the other hand, we're all using computing these days, and in fact, this conversation is taking place on that. And we measure the information that can be held in the hard disk, for example, or the amount of information that can be passing between us, for example, on the internet in this conversation. And we can measure it irrespective of what it's about. We can say, I don't care what it's about. I want to know how many bits per second can be transmitted on this line. And I call that measure a measure of information. But now what I've done is I've backed away from the full concept of information to talk only about, you might say, its medium or signal characteristics. Shannon, as a person working for Bell Telephone Labs at the time, of course, this was a critical issue. And interestingly enough, his background was that before that he was working on encryption during the Second World War. So that dealing with encryption, you don't necessarily know what it's about, but you want to figure out how to organize it in such a way that you can get to its aboutness to some extent. But you can do all kinds of analyses without knowing what it's about. And that allowed technicians at the time to begin to think in these terms, to think of information in terms of just what you might call properties of the medium itself. And so we began to figure out ways, after his work in the 1950s, to actually measure, get a precise measure of things like bandwidth, storage capacity on our various devices, and so on, by mathematical analysis that was quite precise and has made the engineering of all the devices we use today possible, because we can now use it as an engineering feature. The problem is that concept of information gets rid of what information is about. It doesn't get rid of it as much as just ignores it. It says that for the purposes of engineering, it's not necessary. Now, what something is about, as we began in this conversation to struggle with, is not something present. It's not an intrinsic property. So there's what my words are about are not intrinsic to the physics of the sounds that I'm producing, the electrons that are carrying this across to you, for example. It's not an intrinsic feature, not something you can hold on to. So it was very convenient, it seems to me, for this concept of information to become much more influential in the sciences in the last half century of the 20th century. And what happened is, of course, it became a topic for genetics. It became a topic for cognition, for neuroscience, and of course for computing. It even became a way that people talked about evolution and how evolution works as an information process. Because that way of talking about information doesn't seem to force you to talk about this absent stuff. Now, what's interesting is that hidden in Shannon's original analysis was that he was interested in both what you might call how much information can be transmitted on a particular channel and what makes a message different than all the information on that channel. And the distinction had to do with constraint. What he said was that what you want to do when you get information, to get at its aboutness, so to speak, is you have to figure out what information is no longer relevant. What are the possibilities that you can eliminate? That is, what you want to do when you transmit something is you want to eliminate uncertainty. Now, eliminating uncertainty is about creating something absent, constraining something, leaving something out. So implicit in the very notion of information as a signal, you've got normative issues. And by normative, I mean that you can get the information right or wrong. You can do the translation appropriately or inappropriately. But it also means that you have something else in an information channel, and that we may be dealing with here to some extent. Noise. Noise is not intrinsic. Noise is a decision that we have to make about which bits of information are the useful ones and which ones are the unuseful ones. That turns out to force us back into this realm where we're dealing with something absent, something present and something absent. What we want to do is to get rid of the noise and focus on the signal. But of course, if I'm a repair person looking at this electronic instrument, I might want to look at the noise as information to tell me about what's wrong. So that the distinction between a signal that is a message and noise is actually an interpretive decision. It's a decision based upon which constraints you're going to focus on. So what I realized is that to get back to understanding the concept of information in its full sense to make it scientific, to make the aboutness scientific, even though it's something that's not there. It has to do with this relationship to something absent. One needed to use the concept of constraint. That constraint would help us do that. And the link to what we've just been talking about is that homeodynamic processes decrease constraint. Morphodynamic processes increase constraint, make things more regular, eliminate options. But teleodynamic processes preserve constraints. Once they're generated, you don't want them to go. Now, that's, of course, what information is about, what thinking is about, what life is about. And to say that life is an information process, it's not just passing on data. It's maintaining relationships of aboutness to the world. It's maintaining the noise and the signal separately from each other, knowing which is which, making that discernment. We needed a theory of information that brought us back into the world of meaning and significance. And we needed it in the sciences, not just in the humanities. We needed to sort of make absence safe for the sciences. So that's how this fits together with this issue of normativity, of dynamics, of thermodynamics. It's interesting also that, of course, Shannon's theory of information was based upon the same kind of mathematics that is essential to thermodynamics. In fact, his measure of the amount of information that can be carried on a channel, he called the entropy of the channel, because mathematically it's like the same measure that Ludwig Boltzmann used to measure the entropy of a physical system. And so there is an intrinsic relationship between the dynamics, between information in Shannon's sense, and information in the full sense of things that have aboutness and normativity to them.
Okay, so I would like to ask you, how do we get from those physical processes as you've been describing, and particularly from absence and constraints, to a better understanding of how mental phenomena, like, for example, consciousness and the self, occur? I was going to say how they emerge, but I guess that is a very complicated term to use here. So could you tell us about that?
I do think, I'll just say that I think understanding emergence without some of its baggage is important. I would say that my description of morphodynamics and teleodynamics, morphodynamic processes emerge from homeodynamic processes, and teleodynamic processes emerge from morphodynamic processes. And with each of those transitions, new kinds of features come into the world. So particularly with the teleodynamic system, what we're saying is that normative features emerge into the world. There were no normative features without teleodynamic systems in the world. Teleodynamics, because it maintains constraints, can be correct or incorrect, functional or non-functional. So normativity does emerge for the first time any place that teleodynamic processes show up. Only, of course, with respect to those teleodynamic processes. The rest of the world doesn't care whether teleodynamics preserves or not. But the challenge is that it's not going to be a quick jump from simple teleodynamics to minds. And I think we may be a little too anxious to make that move. And I like to tell people, no, let's take it one step at a time, baby steps to get there. We have a long ways to go because, of course, life was around for 3.5 billion years before any kinds of serious minds showed up. And by that I'm talking about maybe dinosaurs and fish and stuff that have brains. They're not minds in the full sense that we would think about it, but certainly beginning to represent the world and possibly having something that we would call consciousness. That takes a long time to show up in evolution, which means that there's a lot of steps between a basic teleodynamic system and this kind of a system. I like to describe it in the following sense. First of all, let's go back to the concept of information. All of life is about maintaining its constraints, and constraints are what maintain the information. Information is embodied in the constraints. That's what Shannon has taught us. And information in the aboutness sense is embodied in constraints. And in the useful sense, it's embodied in constraints because information is only useful if it helps you do something. If you can do some work to accomplish something more efficiently because of the information you've got. Because I have information about the world, I don't have to make certain mistakes. I can use that information to constrain how I interact with the world. And so even usefulness is helped by this concept of constraint. And of course, doing work itself is about constraining the way we allow energy to be released. By doing that, we can change things in a focused way, in a constrained way. So the very concept of work itself is caught up in this concept. The problem is, how do we then go from these fairly basic ideas that should apply all the way down to bacteria, for example, to talk about minds and what mental processes are? Well, first of all, there's many, many steps. But I like to divide it into two different domains. One is to say that even a simple teleodynamic system, like a bacterium, has a kind of sentience. By that I mean that it senses the world. It doesn't have a sense of itself necessarily, but a bacterium or a plant has to respond to its world. It has to be sensitive to what's going on around it and organize itself and reorganize its physiology to compensate for those changes in the world. So using the concept of plants, I like to call this vegetative sentience, as it doesn't have awareness like we would describe it, but it's sensitive to the world, and it's sensitive in a way that is responsive to its own needs. So I like to call this vegetative sentience. And what I would say is that all life exhibits this kind of sentience, vegetative responsiveness to the world with respect to its own normativity. But that's not enough to explain what a brain is, what a mind does. And so the next question is, so what's the difference? My body has vegetative sentience, and in fact, every neuron in my brain has vegetative sentience. It's responding to the disturbances that other neurons are sending to it, that glucose and oxygen are providing around it in its metabolism. Each one of those cells has vegetative sentience. But it's not just that you put a whole bunch of vegetative sentience together and you get me, because that could describe my hand too, or my liver. It's got a whole bunch of vegetative sentience going on there. That's not enough. So the question is, how do we rethink the problem of what brains provide? Because using the term vegetative, I've literally sort of by implication noted that these creatures outside of my window here, these trees and plants and so on, they don't have brains. And as a result, they don't have a certain kind of sentience. And what's the difference? I like to call that difference subjective sentience, which is much more like what a philosopher might call what we're doing. I wouldn't want to call it consciousness necessarily, but certainly what even simple brains provide is a higher order form of sentience. And the question is, what is that higher order form of sentience? And what I realized is that we have to go back and rethink the concept of self. That's really behind this, because vegetative sentience is about a kind of self. It's all about maintaining and reproducing and sustaining a self, oneself, so to speak, even though you don't have a representation independently of what that self is. All of your organization, whether you're a plant or a bacterium, has that kind of organization. Interestingly enough, when you add a brain to an organism, and brains evolved with locomotion ultimately, as they evolved in creatures that have to get around, and therefore predict their environments. Make predictions about environments that they haven't come to yet. They might come to. If you're just rooted to the ground, you just have to deal with what comes at you and maybe predict what's going to change season to season. But if you move, you want to find certain things. You're going towards ends that are of a different sort. And that seems to me to require a different kind of sentience. And what I like to say is that to some extent, it's what I call second order vegetative sentience. And what I mean by that is that it's vegetative sentience, all of my neurons, which are vegetatively sentient, that themselves are sentient collectively about the body that they're in, not just the world around them, not just their immediate neighbors. And so I think brains are also teleodynamically organized in the same sense of self-organizing systems, morphodynamic systems that are reciprocal to each other and create this kind of closure, create this kind of higher order telos. That is now no longer just the body, and one of the reasons we have sort of this Cartesian notion of, a ghost in a machine in our body, is that the environment of the brain is both the body it's in and the world that the body is in. So in a sense, if brains generate a higher order form of teleodynamics, that is by the dynamics of all of these neurons interacting with each other in response to bodies and the surrounding world, then what we've got is what you might call a vegetative sentience of vegetative sentience. So it's a higher order form of vegetative sentience. But that means that vegetative sentience, in a sense, is sentient of its own sentience. And I think that's the distinction that we need to focus on. So those of us that talk about consciousness, or where you find it these days, we're talking about things that typically people do, brains do, and what senses do, and so on and so forth. But we miss this very simple notion that it's about self. If we can't explain why something has self, why there's a form of telos, end-directedness, distinctive to that level of self, then we can't even get started with the explanation. We need to have a locus, an agency. That's what we're after with the concept of self. The key is that we can now see that there is a kind of self, a mode of self that all life has, and an additional mode of self within self that creatures with brains have. Add human beings to this, and we have yet another level of it, which has to do with our symbolic capacities and our ability to do what you and I are doing right now, exchanging ideas, trying to get in each other's heads, so to speak, figuring out what we each want, what we're each thinking, what we each know and don't know, and then react to it. But in that process, there's a sort of higher order perspective on self also that develops, so that we're aware of our own self as reflected in somebody else's self. I like to think of Adam and Eve as having made this discovery because the first thing they do is they hide themselves. They hide their sex organs from each other. They suddenly have discovered that they can be seen by another self. Other animals don't have this for the most part, but I think we do, and this makes it so that it gives us a sort of virtual outside self that we can sort of look at ourselves with respect to. So it's even almost a third level of this process that we human beings have brought into the world. But the core story is still explaining what self is. If you can't explain how self comes into the world from dynamics, you can't even get started.